The fabrication of turbine blades involves several precise machining processes to ensure durability and efficiency. Operations such as drilling, turning, and milling are used to shape the blade profile accurately and prepare it for high-speed, high-temperature environment. Proper machining ensures the blades can perform reliably in demanding turbine system.
I will continue with the next segment, which focus on safety procedure and equipment used during each process. Before any process begins, all students must be in full PPE. This includes wearing faculty jacket that is zipped up completely, sleeves must not be rolled up, and are required to wear proper safety shoes, and for girls, the headscarf must be tucked in. These precautions are basic but crucial to protect us from sharp tools, hot surface, and flying debris. During the drilling process in the Gegas lab, the first thing need to do was wear safety goggles to protect eyes from metal chips. The workpiece was clamped firmly to make sure it didn't move while drilling. Never use your hands to hold the material directly. Make sure that your hands and sleeves were away from the rotating drill. After completing the drilling, turn off the machine before removing the workpiece. For the grinding process, safety was also a top priority. Goggles or a face shield are needed to protect from sparks and flying debris. Students need to wear gloves to protect hands and make sure they was not fitting to avoid getting caught. Stood slightly to the side while switching on the machine just in case anything flew off unexpectedly. Throughout the process, use gentle pressure and avoid forcing the material against the wheel. When using the turning machine, only 1 or 2 persons can operate at a time to stay focused and avoid accident. Always wear goggles for eye protection and keep a safe distance from rotating parts. Make sure that all clothing was tucked in and long hair was tied up to prevent anything from getting caught. Before starting, double check that both the tool and the workpiece were tightly secured. During the milling process, start by wearing goggles to protect from flying metal chips. Carefully clamp the workpiece tightly to prevent movement during cutting. Always keep a safe distance from the rotating cutter and avoid touching any moving parts. Once the process was done, wait for the machine to fully stop and use a brush to clean the surface. In the welding area, full PPE was essential. Wear welding gloves, an apron, a face shield to protect yourself from sparks and UV radiation. Before welding, make sure the area was free from any flammable objects. Welding curtains were placed around the workspace to protect others from arc flash. Please ensure that there are proper ventilation to avoid inhaling toxic fumes from the process.
We begin by marking the workpiece based on the turbine blade and shaft dimensions. Precise measurements were made using a ruler and vernier calipers to ensure accuracy. We cut the material for part 2 and part 3 using hacksaw. This raw cutting helps to insulate each turbine part for further processing. Next, we drill center hole using an R8 drill for part 2 and part 3. This alignment ensures positions in the upcoming turning and threading operations. We continue by drilling specific diameter holes 4 mm for part 2 and 3 mm for part 3. These dimensions match the design and later support the fastener and alignment. And here is the result up until now. Using the milling machine, we perform 3 mm depth cutting for both part 2 and part 3. This step helps define the blade slots and shape the turbine components. For part 3, an additional milling process was done, which is a cut through to accommodate mechanical fitting of blade slotting. Both part 2 and part 3 were turned on the lathe to achieve an outer radius for 27.5 mm. This ensures balance and symmetry for smooth turbine rotation. Part 2 was drilled with countersink to accommodate flathead screw, while part 3 was threading using an M4 hand tab. This allows for precise assembly without welding gaps. These individual parts were then assembled and joined using spot welding. Proper alignment during welding ensures the turbine maintains its shape during operation. Finally, grinding was performed to remove the weld bit, following by polishing for better aesthetic and reduced surface roughness. Surface finishing is vital to prevent corrosion and improve aerodynamics. Mill stick was selected for its strength, weldability, and affordability. Each manufacturing process, which is cutting, milling, lathe, drilling, threading, welding, and polishing, was chosen to match the required precision, surface finish, and mechanical performance of the turbine.
Problem 1. The first problem that we encounter is porosity, which happens during welding process. It is caused by air molecule or gas trapped inside the metal. We managed to solve the problem by cleaning the workpiece and weld it again using the correct technique. Next, we will talk about problem 2. Our problem is we accidentally broke the tools during milling process. This is caused by too much depth of cut and milling speed is too high. So we solve it by using another tools and control our speed and decrease the depth of cut to prevent from breaking it again. We reduce the milling speed by rotating the handle slowly and reduce depth of cut from 1 mm to 0.5 mm. Problem 3. Problem 3, which is screeching noise that occur during turning process. This is caused by too much depth of cut, turning speed is too high, and the workpiece doesn't fit properly in the holder. Our solution is reduce the turning speed, decrease the depth of cut, and fit workpiece tightly to the holder. What is meant by reducing turning speed is to make sure to rotate the handle slow and consistent to achieve better result. By decreasing the depth of cut, we can decrease the friction between the blade and the surface of the workspace. We can also observe if screeching noise or smoke came out during the process and reduce the depth of cut more. Lastly, we need to fit the workpiece at the holder properly. Besides from screeching noise, this can affect the surface finish of the final product. Our last problem that we encounter, which is problem 4. Wrong fitting, which is occur during the measuring process that is caused by wrong measurement. We solve it by using proper tools to measure each workpiece and compare each part if it is more than one and measure it again after the finish. Proper tools such as vernier calipers, protractor and ruler are used to get accurate measurement. If the part is more than one, we can compare each part and observe if there is any difference. Before assembly, make sure to measure based on the actual measurement to avoid from any misfitting. Proper tools.
There were several shortcomings or mistakes that we made throughout the course of completing this task. One of the main issues was that we did not follow the initial plan that had been set. As a result, there were several weeks where our group fell behind compared to the other group. We failed to complete the assigned task during the intended week, which led to delay in our overall progress. In addition, during the milling process, we made a technical mistake by cutting the metal plate beyond the allowed limit, which was 1 mm. This error caused the blade we were using to break and become unusable. To improve on this mistake, we should reorganize our task schedule more systematically and ensure that every group member complete the assigned work according to the timeline. We also need to be more disciplined and following the schedule to prevent further delay. Furthermore, before using any machine, we must properly understand how to operate it. This can be done by referring to manuals, seeking guidance from instructor or assistant engineer, and ensuring that all safety procedures are followed. These mistakes are closely related to what happened in real-world engineering practice. In the engineering industry, proper time management and project planning are crucial to ensure that a project completely on time. Delay in one part of task can affect the entire project timeline. From a technical perspective, compliance with standard operating procedure is critical to ensure safety and prevent equipment damage. Therefore, this experience has taught us to be more careful and better prepared before entering the real-world engineering field.